Cool, cool. So I'm just trying to get like this on YouTube.
Yeah, I'll go up here.
Yeah, probably.
Cool, which season?
Parker one of those.
Which season?
Yeah, probably.
What about you?
Only seen a couple of them, but I haven't seen them in order. I don't remember what. I cut it. You're paired up and ready. Unsuccessful.
Oh, nice. I just had to switch my like YouTube account, and so I just want to make sure everyone has that. And mirror, apply, keep changes. Good enough. There we go. Cool, cool. Looks good. Okay, so I'm Isaac Sloan. Hopefully you can see my screen. Is there like a high-pitched ringing sound in here?
Yeah.
Where'd that come from?
Big buzz.
Okay. Well, cool, cool. Well, I don't think I did that, but anyway, my name is Isaac Sloan, and I'm going to be talking on encryption methods, sort of what encryption is, what it does to your files, and how to further obscure it so that people can't still guess at the content. And I'm going to demo with bitmap images how if you were to encrypt that data, in a lot of cases, you could still make out what the data was beforehand. So let's just start. So let's open up some code here. So currently, let me actually go over to my terminal. So in here, I actually downloaded an image called Superman BMP. If we were to open that, you would see that it is just a Superman logo. We could really use anything. I just chose this one because it's plain black and white, and we should be able to recognize it. If anyone has a better suggestion, we could probably work with that. But so yeah, back to the code. I'm going to just open up. So let's say Superman equals file.open, and then superman.bmp. And I'm just going to call it toSlice so that it returns the bytes instead of trying to pretend it's a string. So now pretty much with a bitmap, I'm not sure when the last time you played with a bitmap is, but essentially what it is in most cases you have a 24-bit bitmap, which means that you have RGB with 8 bits, 1 byte for each one of those colors. Occasionally you also have a third color, which is just black and white, and that pretty much just says this is the dynamic range of that. Currently, we're just using a 24-bit one, RGB, even though it's actually black and white. It's easier to demo encryption when it's a little bit more than just a single bit. So then on top of that, you have a 54-byte header, which tells your computer or your image, whatever is trying to read your image, that this is the aspect ratio, this is the color profile we're using, and probably a few other things. With like you've probably heard of like raw images straight out of a camera. In most cases, those actually are bitmap images, but they don't have a header. So your raw converter would actually say, okay, in the case of like, RW2 from Nikon or whatever, like I know that this is what the layout would be. And it may, I mean, it may have some amount of header, but it's a header that's defined by the company. It's not like a standard header that you would expect. So really, I mean, at the end of the day, even though we think of bitmaps as being this really old file format that like Microsoft Paint used, it's actually still behind most image creation today. Like even if you look at PNGs, if you look at again like all raw photography, or the base point of what a JPEG is trying to accomplish is pretty much just like, if 15 images in a row are white, I'll just make note of that and move on. But still, like, the concept is it's a bitmap. So first we're going to get the headers off of this. And equals 0. Now just tell it start at 0 and give me 54 bytes. So now if I were to put that, we should be able to call this image encryptor. Cool. So in that case, you actually see all the bytes output. We could obviously make those look a little bit better. Value, and I don't know, value dot 2s. Weird. Okay, good. So there you actually see in binary what the headers are. We could display those in hex or whatever. Pretty much they're not going to have any meaning to us in terms of ASCII or anything that makes sense. So, but anyway, we need these headers in order for a bitmap to work. So the general idea here is save the headers before we encrypt it, because encrypting the headers isn't going to do us any good and it's just going to be fake data. And then we'll take the data right here and just say Superman, and then we'll start in this case at 54, and we're going to go to Superman.size minus 54. That would be, yeah, that's as many bytes as we need to go forward to the end. So now we have both data and yeah, so now we have both the headers and the data. So now what we're going to do is actually just talk about a really simple encryption format. So like in the beginning of digital encryption, pretty much the first idea that anybody came up with was, why don't we just take every single byte and XOR it against another byte? And then we'll have a completely different value. And the only way anybody could figure out what the original value was if they had the original value they XORed it against. So let's just write that really quick and just call that like simple encrypt. And I feel like that's not how you spell that, but so I'll just say data and pass in bytes, and then I'll say password or secret and also bytes, and also it's going to return bytes. So now what we're going to do is we're just going to say data, and then we're going to map with index, and that will give us, I'll just say byte, and then I'll put index. And then right here, I'm going to say B, and I'm going to XOR that with secret. And then I'm going to take I and modulus that against secret.size. So then that way, what's actually going to happen is regardless of the size of the key we have, it's going to start with the first byte of your data, and it's going to XOR that against the first byte of your key. And so on till the end of your key, at which point, because of the modulus, it will start over again at 0. And honestly, that's probably done, unless anybody sees like a problem with it. So now what we're going to do is just open another file, file.open, and we're going to say Superman simple.bmp. I'm going to say that it's open for writing. And then now we'll say file.write. The first thing we're going to write is the headers so that it will know what the data is and that it can actually display it in an image viewer. So here we have the headers. And now I'm going to say f.write and actually pass in simple encrypt and pass in data to simple encrypt plus I guess a password. So I'm not quite sure how many strings that is, but I mean it's a few characters. So I mean in this case, our encryption method is pretty much completely based on how long of a password we gave it. Like we would be extremely encrypted if we gave it a password that was as long as the bytes we were trying to encrypt. But I mean that's pretty much never going to happen. So we're still going to see a pretty obvious pattern in this one. So let's actually run this and see what happens. Possibly it will just blow up, but looks like it worked. So back over to Nautilus. So now you see we actually have this bitmap image that we just created. If I were to open that, as you can see, it no longer looks like it used to. And you can actually see on the edges where like the length of the key takes those blocks and kind of merges them together. So you no longer have this defined line. Every single one of those bytes is drastically different than it used to be, but still looking at it visually, we can still see a very clear pattern. So clearly this isn't the strongest encryption method. If we can see this in a bitmap with ASCII, it's not going to be obvious to our eyes, but a computer program, some sort of machine learning algorithm could probably look at that and say, there's a clear pattern here. And I mean, another problem with this is if you were to actually take some of the bytes in here and actually say, okay, where does it, this whole thing is white. So we could look at this and we could say, with every byte, where does the sequence repeat again? And then once we saw where the sequence started repeating again, we could take that entire block right there, and then we could say, we assume this is white. You could XOR that against the value for white, or FF in the case of hex, right? And you would actually, if you had the right number of blocks that you were doing, you would actually output the key at that point, which probably isn't what you're looking for, unless obviously you're trying to get the key. So let's just move on. So if we were to, you raise your hand? Okay. Okay, so let's go back and actually look at the code. We're going to be using OpenSSL cipher for the rest of this talk. If you actually were to go into your terminal, you could type like OpenSSL and then encryption, and then you could type ciphers, and this will actually give you a list of available ciphers. Is this too small, by the way? Can maybe make it bigger. Unfortunately, I don't know how to do that in Linux, so I mean, whatever. I mean, there's probably a way. Whatever, that's a terminal. Hopefully the code looks good enough. But anyway, there's this big list of ciphers, and I could at least full screen this so you can see them better. The family we're mostly going to be talking about today are the AES ciphers. The first one we're going to be starting with is going to be EES EBC, which is pretty much a slightly newer version of Blowfish. And it's like Blowfish. It also probably shouldn't be used for encryption today. But it actually still is used for encryption a lot, even including a lot of your OpenSSL or just SSL in general. Like in order to use like Internet Explorer, even back to like version 8, you still actually have to use this cipher. So let me open that up again. And then EBS dot. Let me just copy something really fast so I don't have to rewrite my encryption method. Cool, so now I have another encryption method. This one right here, let's just walk through it. I'm taking in bytes, the same as before. I'm also taking a secret. In this case, it's a string. I guess I probably should make that the same, but. And then I'm taking in the algorithm, which is what version of the cipher I'm going to use. I'm defaulting this to AES 256 CBC and defaulting the password just to this. And then on the cipher, I'm actually using OpenSSL cipher, and I'm setting it up with the algorithm that was passed in here. I'm then telling the cipher that it's going to be encrypting instead of decrypting, and it's setting that flag. This is all based on the C library, so pretty much any language you do this in is going to look very similar. Now right here, I'm telling the cipher that the key is secret plus, so the reason I'm doing this is because AES 256 of any kind requires a 32-byte key. So if somebody were to pass a password in this case, that isn't 32 bytes, I'm just telling it, give me the secret plus 0 to 32 minus the secret size, and then joining it as a string. So I'm able to get the right size even if they don't pass it in. Obviously, it's not as secure if we can guess like half of the password, but unless somebody sees this code, they don't know that. And that's not the point of this talk. So now let's talk about the initialization vector. You've probably seen this in a lot of encryption. What this actually is a method to obscure the encryption. So like in the past, we took the key and we applied the key to blocks. And that changed all of the values of the block that we were looking at. But a pattern still remained. So the idea of an initialization vector is that the starting point is always going to be different. And so after you encrypt it with the key, you're then taking another block and you're XORing it against that all the way down to the very bottom. So even if you knew what the key is, the initialization vector is obscuring that further. And everything in the AES family is using that. However, the ways it uses it are drastically different. So then if we come down to right here, all I'm creating here is just an IO so that I can just store all these bytes together before I use them. So I'm creating an IO here called encrypted data. And then I'm taking encrypted data and I'm writing to it the output of the cipher after it updates the value to be encrypted. And then I'm coming down here and pulling the final block off of the cipher, which is pretty much going to be anything remaining after the block size has So I mean, what it's going to do in this case is find 32 byte blocks and go all the way down to the end of the file. At the end of the file, you're probably going to have like 7 bytes that don't fit in. It's then going to take those and return them on final with a bunch of like padded space afterwards. So that's why we're calling .final. And then I'm just calling .slice again to return all of these values from memory as a single array of bytes primarily. It's a bit different than array because it can't be resized like an array. It's just a block in memory of bytes, which are unsigned integers unsigned like 8-bit integers. So that's what this encrypt is going to return in the same way that this one also returned that. I'll just make it clearer and put bytes there. So then if I were to come down here, it'd probably mostly copy this code. And instead of simple, I'm going to say ECB. And then I'm going to, the password should So I'm going to say AES 256 ECB. And this one, since it's converting it to the slice inside, I won't worry about actually converting it to a slice first. Even though that annoys me, maybe I should just, no. Because I still need to make sure it's the right size there. So unless I want to, I don't know, it's fine. So headers, cool. So now I have this data. I don't want to call simple encrypt anymore. I want to just actually call encrypt. And that should be everything necessary. So now I'm going to just save that and run it again. And go back here. And now here we have the ECB one. If everything went right, this should look a tiny bit better. So as you see, we still actually can make out what the image is, but the edges are far more obscure. And that's because we have this 32 block byte, or 32 byte block that is bleeding into all of these edges. So when we encrypt that entire block and flip it, then we actually end up with this kind of really fuzzy outline. And then once you get into solid black or solid white area, it still looks exactly the same as it did in the last encryption method. Does anyone have any questions about that? Cool, let's move on to a different encryption method, which would be, so in this case, let's just do CBC. And this one is actually still considered to be pretty safe to use and one of the stronger encryption methods still used by SSL. So what this one actually does, instead of just taking the initialization vector and applying it to every block, is it actually takes the initialization vector and applies it to the first block, and then it takes the result of that and applies it as the initialization vector to the next block, and so on. So then while you still are encrypting your keys, you're still encrypting your blocks with the same key, the initialization vector is changing every single time. So even if the resulting value of the key and the block that was encrypted ends up being exactly the same as the previous block, it ends up looking way different. So let's just run that. And guess over here. And CBC right here. So you'd be hard pressed to find any kind of pattern in that one. Yeah, best case scenario looks like a TV with the antenna got cut off of. So another one that's actually a really good one to use right now would be the CTR one, which I'm not actually 100% sure on what the difference is between how the initialization of vector is applied with the CTR versus the CBC. The result seems extremely similar, and I know that it is using the result of the last one to modify that in some way. It might be even taking that a step further. The result is generally the same though. So yeah, I kind of got through that actually faster than I thought I would. Does anyone have any questions about any of this?
The CTR versus the CBC, do you know if like one's more efficient than the other as far as like time to encrypt?
I do know that CTR is more efficient than CBC on a multi-core processor. And for everything I've read, that seems to be the primary reason you would use CTR over CBC, is that you could encrypt faster because it uses all of your cores, whereas CBC is single-threaded. So yeah, sorry about talking too fast or something. Yeah.
How did you get into this?
Like I'm a programmer and I need to know about encryptions, and bytes are fun. And I mean, we've kind of spent a lot of our days thinking in terms of encryptions and which encryptions are weak and which ones are strong and what ones we should use. But most of that is just because you read a blog about it somewhere or whatever. So it seemed like it would be a good idea to actually kind of sit down and try to figure out what it was that like the recommended ones were doing and the less recommended ones were doing, and figure out like why it would be easier to break one than the other. And then again, just bytes are fun. I do. Okay.
This is written in Crystal.
It's written in Crystal. It would be very similar in Ruby. The reason I do it in Crystal is because the only way to store bytes in Ruby is actually as a string. And I don't like storing bytes in strings because they're not UTF-8 characters, obviously. And because of the fact that storing them as a string, in order to actually utilize them, you're having to call other accessor methods to separate them. Whereas like here, I can basically just treat it as an array. But I mean, most of this logic, I mean, for instance, like this encrypt method right here would look, I guess, minus the IO memory part. But in terms of like the cipher logic there, that would be exactly the same. And yeah, so this is Crystal. I mean, I just wrote it in Crystal because I like how Crystal works, and bytes are easier to use in Crystal. If you, again, I mean, a lot of this is using C libraries and would look the same regardless. The logic up here, theoretically, assuming you had an array of bytes in Ruby, which you could turn a string into, you could treat that logic in pretty much exactly the same way. You could also go through and XOR in exactly the same way with like map with index. You would just have to change the string to an array first. And then like obviously file open, like, I mean, that's exactly what you would expect from Ruby as well, so. Yeah, I actually started writing this in Ruby, but just the encryption was taking longer, so I had to wait a bit longer before I could demo stuff when I was running it. And also, I like the like explicit nature of being able to actually say this will only take bytes.
Is that why you thought this was going to take 2 hours? Because that's how long Ruby was taking to encrypt?
Well, it wasn't taking that long, but I mean.
Do you still have the Ruby version of this, or did you just throw that away?
I think I had it on my MacBook. I mean, theoretically, I mean, I'll share this code, and I mean, there's not going to be a ton of differences because I mean, they're still going to read this, and then it's going to be a string, and it's just going to be like /x and then like some hex value, and it's going, so you'll have to just divide all that up, and at that point, you should technically have an array of bytes, so that's probably going to say they're chars, and that will be annoying, and so you'll have to change them to like an unsigned integer. And Ruby like doesn't really care if something's an unsigned integer or not. It just is like, here's an integer. So I mean, honestly, I bet it's about the same amount of code. And if anybody wanted to actually work on that, like they could message it to me, and I would help them fix it or whatever. So anyway, like here we could pretty much try like any of these codes. I mean, I think I should be able to just throw CTR on here as well. And, we could benchmark this or something if we wanted to against the two different ones. But Crystal, cool. So back to 5. And, okay, so there's CTR. So again, pretty much exactly the same. Like my understanding is that CTR is more useful if you have a lot of cores.
Difference again, I didn't catch how CTR works, but you said the CBC takes the initialization vector and does it for the first block, and then it takes from the first block, does it to the second, and recursively man it. But how does CTR does it?
A CTR is doing the exact same thing, but it's actually starting at like quite a few different locations. So it's taking that initialization vector and it's like, say, starting on the first block and then maybe saying like, let's go to the 100th block. And I can't remember, I read the data sheet on that, but I can't remember how it's choosing like what the next block it's going to start on is. But basically it's taking your image and it's dividing it up into a certain amount of blocks. And it's saying, I'm going to start with the initialization vector on block 0, and then also on like block like 600 and so on, based on how many threads it's actually running, and then going to the end of that. So that in theory, it's pretty much the same, and it shouldn't really be much more secure, even though there is a tiny, tiny bit more duplication. The likelihood that like the IV is obscuring the same block it was on block 0 is pretty low, and even if it was, it's so small you're not going to notice it if it's just like 3 times. So yeah, anyway, don't use ECB or write your own encryption. You know. But writing your own encryption is fun, so I mean, if you want to do it, still do it. And also, Linux computers are pretty cool. You should think about it. You can like hit a key and see everything, and then just go touch the one you want. Your touch bar can't do that. But seriously, any other questions, or should we just talk about TV shows more? Oh, hey, Moy.
Hey. Have you done anything with cryptocurrencies in relation to encryption?
No.
What do you think they use? Are you familiar with what they're using to encrypt any or something? Like any? I don't know.
No, I'm not. I honestly haven't read anything on that. I know terms such as blockchain and stuff. I don't know like fully what those blocks are made out of and what they're chained and how they're encrypted and why.
You should make your own Bitcoin. I'll buy it.
Maybe at some point. As soon as I can get a video card. But yeah, you had a question as well?
So, kind of away from this, going back to just crystal, I know like a little bit about crystal. I was just wondering your take on what it is, what it's like, what is the difference. I heard that Ruby and crystal are very similar.
Well, I mean, as you can see, they are fairly similar. Crystal is statically typed, whereas Ruby isn't statically typed. Ruby's more like duck typed. So it's like behind the scenes, it actually, an object is an object. And if that ever changes, it's actually a pointer to a new object. So like in that case, like it is actually strongly typed, but you're not defining those types. That's happening behind the scenes. So that's giving you quite a bit of speed in terms of performance. Some things it's actually a little bit harder in, obviously, is because you're actually defining what the size of your variables are, such as like, you know, an int 32 or an int 8 or an unsigned int 8 or float or whatever. You're actually defining these sizes, and every single one of your images, every single one of your numbers, regardless of how big it is actually taking up that many bytes. So if you say like, I have a 64-bit integer, that's actually taking up 64 bits. So, which is, you know, quite a bit of space. And even if you only store like the number 3 or something in it, it's still taking up 64 bits. And So you have to be kind of careful. What are the variables that you're using? That being said, I mean, you're still going, even if you were to say use the biggest one for everything, you're still probably going to use less memory than a dynamically interpreted language. Just, I mean, interpreting pretty much across the board takes a lot of memory. So, but that being said, you don't want to just say use the biggest one here, because it will still be less memory, because it's going to be slower and it's going to be more memory than it needs to be. So you do have to think in terms of what is the size that I'm using. If you were to multiply two int32s together and try to store it in another int32, you know, like value A times equals value B, you're at some point going to overflow. And you're going to end up with a problem that like the number ends up looking negative or something crazy, just completely the wrong number, because you can't actually fit that size of a number in the variable that you chose. So, I mean, that's going to be a thing you're going to run into with, you know, any compiled language, really. So, I mean, it isn't Ruby, but syntactically, there's a lot of similarities, and it's way faster. Like, you know, I mean, as it currently stands, like Ruby 2.5 and PHP 7 are basically neck and neck. Whereas like you compile the exact same thing into Crystal and you end up being about 35 times faster than either. So that's kind of an example of why you might want to use Crystal. Obviously, Ruby and PHP have way more people using them. And as such, there's more libraries. You have no guarantee those libraries were well written, but like, they exist and at least worked for some version of your language. Crystal has actually a really good community, and I mean, there's a lot of software that has been written in Crystal, weirdly, for how young of a language it is. I mean, you go to like the Awesome Crystal page on, you know, on GitHub, just say Awesome Crystal, I guess. And there's almost as much stuff there as there is on like Awesome Rust or Awesome D, or languages that are way older. And also, Googling crystals is kind of hard sometimes because of crystals, but but anyway, so like here's basically just the categories, and you see there's already a lot of categories, and then when you actually like scroll through it, there's a lot of stuff there, and pretty much they've recently gone through and weeded everything out that hasn't been maintained. So like everything in here actually works with the latest version of Crystal as well. So I mean, there's just a lot of libraries, which like if you go and look at Rust, like there are a lot of libraries in some fields, but like half of what I care about like just doesn't even exist, like in terms of like any sort of like web framework that's easier to use than like C. Or ORMs or templating languages or anything. Whereas, I mean, just in here, just like even for like HTML or JSON templating, there's a lot of really useful languages, or HTTP or PDF or SAS. I'm just kind of randomly clicking on things. But I mean, for instance, just like with database drivers, oh man, my boss is calling me. Stop it. Hello, did that answer it? Cool. I think I'm good. So back to the internet. So yeah, just with like database drivers and clients, like, you know, there's quite a few of them, and there's more being written every day. And some of them aren't listed here because they're not like fully written. But I mean, most of the ones that you can think of are there.
Does Crystal have a...
Yeah. I mean, there's actually quite a few. I mean, obviously, I'll try to convince you that you should use like Amber, because I've been part of the core team and written a lot of this. But that being said, I mean, this isn't the only one. There's this is a really easy to use one, and it has a really good CLI. But you also have Camel, which is basically Sinatra. I don't know if you're familiar with Sinatra. It's a really simple framework. Pretty much the concept is you define your route like, you know, get slash and then return hello world, or socket, and this is what you send, or you know, post slash listings and take a new listing as a post request and store it somewhere. It's not really a framework in that, like, it doesn't give you much else. You choose which ORMs you use, you choose which template renderers you're using, like pretty much everything. But in terms of just like basically think of it as a router. And I mean, it's, you know, it works fairly well and is fairly fast. I mean, I don't know, I guess he's showing on his like MacBook Pro 2013, he's getting about 100 million requests a second versus like about I don't know, 3,000 or something in Sinatra. And that's about similar with what we're getting in Amber too. Although if you turn on like session encryption and CSRF and Flash and like everything you can think of in terms of like handlers, like that is slowing you down somewhat. And I mean, I've talked in Amber before, and I'll definitely talk in Amber again. But I mean, definitely go and look at like the Amber framework. We have pretty decent documents and pretty decent. It's a pretty decent documentation, and there's quite a few like Gitter channels and stuff that people answer questions on pretty fast. So yeah, there's also this new one called a Lucky Framework. And personally, I'm kind of, I don't know, I have a little bit of a beef with this because they stole like a ton of our code and just like announced that like they had written this new framework that was super awesome. And it's cool because I think it brings more people to Crystal, and that's good. Personally, I don't really like most of the philosophy of the framework. They don't really give you any sort of standard like HTML templating. You actually write all of your HTML in Crystal, like basically an XML or JBuilder sort of like concept, which I've never been a fan of. Obviously, the guy who wrote it thinks it's cool, and he's managed to get quite a few people to come over and start his GitHub. He works at Thoughtbot, and obviously Thoughtbot has a pretty big reputation, so that obviously helps. So these are the three current frameworks that are actually actively being developed and maintained. And I mean, honestly, all of them are better than like what you find in like Rust, which has pretty much Diesel and a couple others. But so yeah, definitely check out Amber though. It's orange and also star it. Yeah, go go to GitHub and star Amber. We want to have over 1,000 stars someday. I've never had an open source project with 1,000 stars before, so sort of a bucket list. Oh, it's 830. There. Went away. There we go.
8:30 left. Just gave you.
Awesome. Here, I better refresh. There we go. Thank you. Yeah, so like just in terms of like trying to learn and getting a job and all that, I mean, probably just you already have enough things to learn, but like Crystal is super fun, fairly similar to Ruby, and crazy fast. So that's pretty much why you should or shouldn't use it. Well, cool. Thanks for coming, everyone.
pretty much my whole life. I was born and raised there. So are you from there?
I lived down there.
Okay. Did you work there?